You unlock this door with the key of chemistry. Beyond it is another dimension, a dimension of surface tension, a dimension of cohesion, a dimension of vapor pressure. You're moving into a land of both inter and intra. Things and ideas. You just crossed into the IMF zone. Today's episode, the IMF Continuum. Okay, so, hi everyone. I'm Sophia, and I'm going to be teaching you all about the IMF Continuum today. Alright, so first off, this presentation is based on the idea that you guys already know about IMFs and their different definitions and how to identify them. If you don't, please find another video to learn how to do that. Okay, so the IMFs can actually be ordered from weakest to strongest, and as you can see, we have our weakest force at the bottom being the London force, followed by the polar, then H-bond, and then we move up to metallic and ionic, which are about the same strength, and at the very top, the strongest is network. Awesome. Alright, so melting and boiling points are based on this continuum. So the lowest boiling point is where the weakest IMFs are, and things that have the higher boiling or melting points are where the strongest IMFs are. So network structures will have a lot higher boiling points than, let's say, London's, and a metallic would have a much higher melting point than, let's say, a polar. Okay, and it actually makes a lot of sense if you think about why. So you would think that all these stronger forces at the top, like network, they need a higher boiling point in order to, a higher temperature is needed in order to break apart the very, very strong IMF. It kind of makes sense. And something like London, which doesn't have as much strength, doesn't need as high of or low of a temperature to break it apart in order to melt it or boil it. Awesome. And London forces, there's actually kind of, I guess, a mini continuum with the London forces, which is when they have larger molecules or more electrons, they are more polarizable, which I guess if you think about it, the stronger ones would be like, let's say up here, which are closer to polar, so I guess more polarizable. And that means that even if, let's say, you have two things that are both London, one of them could have a higher melting point if they have more electrons. Awesome. So let's move on to the next one, which is surface tension. And surface tension is the skin of a liquid at the surface due to the 3D IMF structure being interrupted. So a way to think about this is if you've ever left a gravy boat out, the gravy gets like this, gross skin at the top, and that's kind of a way to see surface tension. Okay, so surface tension actually only goes up to the H bonds. So it only goes up to the intermolecular forces. And the highest is the H bond, and things with low surface tension would be London. And if you guys can also remember back to this kind of mini lab we did, we had a jar of water and we placed a paper clip in it. And the paper clip was actually able to rest kind of just below the surface of the water because the surface tension was holding that paper clip up. Alright, so our next thing is viscosity. And viscosity is the resistance to flow. So if you think about a thicker kind of liquid, it will have more of a resistance to flow and move around. Or if you think about a liquid that's really, really runny and thin, it'll move around really, really easily. It doesn't have much of a resistance to flow. Okay, so just like surface tension, viscosity only goes through our intermolecular forces. So the highest is H bond, and our lowest is London. Alright, so our next one is adhesion and cohesion. These ones sound kind of similar, so make sure you don't mix them up. So adhesion is the ability to stick to another substance. So when Spider-Man jumps on a wall, he's having adhesion. He can stick to the wall. A way to remember this is if you remember tape, it's adhesive tape because that tape can stick to other substances. Something very similar is cohesion. And cohesion is the tendency to stick to the same nearby molecule. So if you remember back to the time when we dropped water on coins, and the water was actually able to kind of form like a mini half bubble on top of the coin, we were able to put a lot of drops on, and that's because the water molecules are cohesive, so they're sticking to each other in order to stay on that coin. And something pretty much, if it's adhesive, it will always be cohesive as well. And just like our other ones, this one only goes through the intermolecular forces. They're the only ones who experience it, and the highest are H bond, just like all the other ones, surprise, surprise, and the lowest is with London. Alright, so our next one is evaporation rate. A lot of you have probably already heard about evaporation. Is when, let's say, you left a jar of water out. It's the reason why that when you come back after a long time, the water level will have decreased because the liquid in the jar evaporated into the air. Okay? And so, just like all of our other ones, it only goes through the intermolecular forces. However, what's a little bit different is at the top here by H bond, it has a slow evaporation rate, and at the bottom by London, it has a fast evaporation rate. And if we sit down and think about this, it makes kind of a lot of sense. Something that is stronger, like H bond, takes a while for something to break down and evaporate into the air. It makes kind of logical sense. So that's why it has a slower evaporation rate. And something like London, which is not so strong, can break apart and evaporate into the air fast. Alright, and our next one is vapor pressure, which kind of throws us all for a loop, because if you can see over here, up top by our H bond is actually where it's lowest, and down here by our London is where it's highest. But let's back up a second and define it. Vapor pressure is evaporation pressure from a liquid creating vapor in a closed container. So it sounds kind of scientifical, but if you think about, let's say, a water bottle that you left out in the heat, it gets inside kind of little water droplets, and because it's trying to get out, it's trying to evaporate, but it's in a closed container. So that's what vapor pressure is. And vapor, if you want a definition for it, is it's a gas that should be a liquid or a solid. Okay, so now moving over to our continuum over here, it kind of goes hand in hand with evaporation. Just like how evaporation was slow up top by H bond, so too is vapor pressure. It has low vapor pressure by the H bond, and going down the continuum down to H, it has a higher vapor pressure because it's able to do it more quickly. Alright, so now we're going to do an example. So this is a question that you could see on your midterm coming up, or any kind of quiz and test, where we would use our knowledge of the IMF continuum in order to answer a question. So here we have two things. We have CCl4 and H2O. Alright, and you would probably ask something like, which has a greater boiling point? So let's find out what kind of IMFs these things are experiencing. So to figure out CCl4, we would draw a Lewis dot structure. So CCl4's Lewis dot structure looks something like this. Alright. Now we gotta put our little electrons on. Sorry, they're little tiny dots. Okay. Dot 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 dot. Alright, so we can see since there's no lone electron pairs on the central atom and it's balanced, that it is a London, that it's experiencing London. London. Now, we don't have to draw a Lewis dot structure for this H2O because we can tell that since it has hydrogen with either FO or N, here it's O, that it is an H bond. Which means since it's experiencing hydrogen bonding, that it also has polar and London at the same time. And since we know from our continuum that H bonds have a higher boiling point because it's a stronger IMF than London, we know that H2O would have a greater boiling point. It's just that easy. Also keep in mind that if you ever run into a problem where they're both London, and so you would think that since they're both London, they have the same boiling point, you actually want to take a second and look at which one has a greater number of electrons. And whichever one has a greater number of electrons means that it has a larger molecular size, and if you can remember, we said that they're more polarizable, and therefore that one with the greater molecular size, which is more polarizable, would have a higher boiling point than the other one. So just remember that if you ever run into a problem like that. All right, and the end. Thanks for listening.